In this lecture, we will discuss solutions to linear equations. As we saw in the previous lecture, we had established the importance of matrix theory and linear algebra in data sciences. The concepts that we covered previously are data representation using matrices, and from a matrix of data, we saw how to identify linear relationships, if any, among the variables or attributes. We saw that we could establish these linear relationships using the concept of null space. In this lecture, we will focus on the next important topic of extracting solutions for matrix equations, which is the most fundamental aspect of data science, where we might have several equations and we might have to find solutions to those equations. So, we will look at solving matrix equations. In general, when we have a set of linear equations, when we write it in the matrix form, we write this in a form Ax equal to b, where A is generally a matrix of size m by n, and as we saw in the last class, m would represent the number of rows and n would represent the number of columns. And for matrix multiplication to work, x has to be of size n by 1 and b has to be of size m by 1. Now, if you take each row of this equation, you will have a left hand side and a right hand side, and the left hand side will have terms corresponding to multiplying the first row of A with x, and the right hand side will have the term corresponding to b's. If you take the first row, it will be the first equation and so on. So, from that viewpoint, m represents the number of equations in the system of equations and n represents the number of variables, and in general b is the constant matrix that is used on the right hand side. So, when we write Ax equal to b, this represents a set of m equations in n variables. Now, clearly there are three cases that one needs to address. When m equals n, that means the number of equations and variables are the same. So, this turns out to be the easiest case to solve. When m is greater than n, that means we have more equations than variables. So, we might not have enough variables to satisfy all the equations. In the usual case, this will lead to no solution. When m is less than n, the number of equations are less than the number of variables. What this basically means is that we have lot more variables than necessary to solve the given set of equations. So, in a general case, this will usually lead to multiple solutions. So, the first case is the easiest to solve, the second case does not have solution usually, and the third case has multiple solutions. What we are going to do is we are going to look into these cases independently and then combine all of them using the concept of pseudo inverse. We had already discussed the concept of rank in the previous lecture, but let us talk about it again, because this is going to be useful as we talk about solving equations. If you consider a matrix A m by n, now if all the rows of the matrix are linearly independent, then remember we said the rows represent data. So, this basically means that the data sampling does not present a linear relationship, that is, the samples are independent of each other. Now, when all the columns of the matrix are linearly independent, that basically means the variables are linearly independent, because columns represent variable. In a general case, if I have a matrix m by n, if m is smaller than n, the maximum rank of the matrix can only be m. So, the maximum rank can be the less of the two numbers. So, in cases where I have a matrix m by n, where n is smaller than m, then the maximum rank that is possible is n. In general, whatever be the size of the matrix, it has been established that row rank is equal to column rank. So, you cannot have a different row rank and column rank. What it basically means is, whatever be the size of the matrix, if you have a certain number of independent rows, you will have only those many numbers of independent columns and so on. So, this is something important to bear in mind. Now, let us look at the case of m equal to n, that is we have the same number of equations and variables. If A is full rank, what does full rank mean? Now, we have the same number of equations and variables m equal to n. So, the rank of the maximum rank of the matrix can be m or n, because both are the same. Now, if the rank of the matrix turns out to be m, then it is what is called a full rank matrix. What this basically means, that all of these equations on the left hand side are independent of each other. In other words, you can never get any equation on the left hand side as a linear combination of other equations on the left hand side. In this case, there is a unique solution to the Ax equal to b problem, and that unique solution is x equal to A inverse b. Now, from your high school and so on, you would have learned that if the determinant is not 0, A inverse is possible to compute. So, one could simply compute x equal to A inverse b as a solution to this problem. The difficulty arises only when A is not full rank. That means, the rank of the matrix is less than m. In this case, what it means is, if I take the left hand side of the equation Ax equal to b and then make some linear combinations of some rows of A, at least one of the rows of A is going to be a linear combination of the other rows of A. That is the reason why the rank of the matrix became less than m. In this case, depending on what the values are on the right hand side, you could have two situations. One situation is what we are going to call as a consistent situation. I will explain this through an example in later slides. When you have a consistent situation, then you will have infinite number of solutions. There could be many solutions for Ax equal to b, and in the case where the system of equations become inconsistent, there will be no solution to this problem. So, to summarize, when m equal to n, this is what is called a square matrix, and if the matrix is full rank, determinant A not equal to 0, then there is an unique solution x equal to A inverse b, and when A is not full rank, there are two situations that are possible. One is what we call as a consistent scenario, where we could have infinite solutions, and the other one is what is called the inconsistent scenario, where we might have no solution. Let us take a simple example where I have on the top of the screen the matrix in the form A x equal to b. In this case, matrix A is 1 3 2 4, x is x1 x2 7 10. So, you can notice that there are two equations in two variables x1 and x2. The first equation is basically x1 plus 3 x2 equal to 7, and the second equation is 2 x1 plus 4 x2 equals 10. We can see that this is full rank, because whatever multiple of the first column you take, you can never represent the second column, and similarly whatever multiple of the first row you take, you can never represent the second row. And this can also be seen from the fact that the determinant of A is not 0. From your high school, you know the determinant is going to be in this case simply 4 times 1 minus 2 times 3. So, this is not 0. So, rank of A is 2. So, we have maximum rank, that matrix size is 2 by 2 and the rank is 2. So, this implies that the matrix is full rank. Now, we said in the previous slide that x1 x2 can be written as A inverse b. So, this is the A inverse matrix 1 3 2 4, this inverse b. You can do an inverse computation and then calculate the solution as 1 2. And if we put this solution back into the equation, you will see 1 times 2 plus 1 times 1 plus 3 times 2 is 7, and 2 times 1 plus 4 times 2 is 10. So, the solution 1 2 satisfies this equation. Now, if you want to write a R code for this, it is very simple. You write A matrix, put the numbers in C and then define the number of columns. You define what B is and then simply use the command solve for x to get the solution, and as you notice here, the solution is 1 2. So, this is a case of full rank where I get an unique solution. The important thing to note here is no other solution will be able to satisfy these two equations. Now, let us take another example to illustrate what happens when the rows or columns become linearly dependent. So, here is another set of equations and we have to read these equations as x 1 plus 2 x 2 is 5 and 2 x 1 plus 4 x 2 equals 10. Now, if you notice these equations through the matrix A, you will see that if I multiply the first column by 2, I get the second column. So, the second column is linearly dependent on the first column or the first column is linearly dependent on the second column, whichever way you want to say it. Similarly, if you divide, for example, the second row by 2, you will get the first row, or if you multiply the first row by 2, you will get the second row. So, the rows are also linearly dependent, and as I said before, there is only one linearly independent column, and that necessarily means that there will be only one linearly independent row. Now, another way to check this linear dependence is to calculate the determinant of this matrix, and when we calculate the determinant of this matrix, you will get 1 times 4 minus 2 times 2, which is 4 minus 4, which is 0. So, determinant also says there is linear dependence here, and from the previous lecture we know that when the rank is 1 and the number of columns are 2, the nullity is 1. So, there is one vector in the null space. Now, let us look at the equations. When you write these equations, as I said before, the first equation x 1 plus 2 x 2 equals 5 and the second equation is 2 x 1 plus 4 x 2 equals 10. When we talk about the linear dependence of the rows of A, we are only talking about the left hand side, we never talked about the right hand side. Now, whenever the left hand side becomes linearly dependent, if the same linear dependence is maintained on the right hand side also, then we have the situation of consistent equations. So, if we take a look at this example, we know the left hand side, if I take the first equation and multiply it by 2, I get the second equation on the left hand side. So, x 1 plus 2 x 2 multiplied by 2 gives me 2 x 1 plus 4 x 2. Now, if the same linear dependence is maintained on the right hand side, that is, if I take the first number 5 and multiply it by 2, I should get this number. In this case, we have constructed this example in such a way that we get this number. Now, not only is the left hand side linearly dependent, the same linear dependence is also maintained on the right hand side. So, as a whole, the equations become consistent, but linearly dependent on each other. So, in this case, you notice that if I solve this equation, I do not have to solve this equation, because I multiply this by 2, I get this equation. So, whatever x 1 and x 2 will solve that equation will also solve the second equation. So, I can drop one of these two equations. Let us assume I drop this equation out. So, I am just left with x 1 plus 2 x 2 equal to 5. But now, notice that I have one equation in two variables. That basically tells me I have one free variable. So, for example, if I take this equation x 1 plus 2 x 2 equals 5, if I set x 2 equals 0, I get x 1 equals 5. If I set x 2 equals 1, I get x 1 equal 3 and so on. So, all of these are solutions to this equation. I am just pointing out to 2. Now, you can notice that I can take any value for x 2 and then calculate an x 1 which will satisfy this equation. Since I can take any value for x 2, there are infinite choices for x 2. Corresponding to each one of these infinite choices, I will get a value of x 1. So, that pair would be a solution to this set of equations. So, when this A becomes rank less than full rank, if the equations are consistent, then we will get infinitely many solutions. Let us take another example to explain the idea of inconsistent equations. Let us look at this example here. This is the same example as the previous case, except for one change. This number has been changed from 10 to 9. In the previous case, we saw that the left hand side, if I multiply the first equation by 2, I get the second equation. And since in the previous example this number was 10, when I multiplied 5 by 2 I get 10. So, both the equations became consistent and I could drop one equation. However, if this number was anything other than 10, then what it basically means is that while the left hand side will be linearly dependent, where the second equation will be twice the first equation, the right hand side will always be inconsistent if this number is not 10. That basically means whatever x1 and x2 values that you used for solving the first equation, if you plug that value into the second equation, your right hand side will always be 10, but you want it to be 9. So, which is never possible. So, this is a case where you will not have any solution. So, in other words, if this number is anything other than 10, you will have no solution to these equations. This will become a inconsistent case. Now, again inconsistent case is possible only when the rank of the matrix is less than full rank, that is there are some rows which are linearly dependent on the left hand side, which you can again verify by the same determinant 1 times 4 minus 2 times 2 is 0. And since the second row is inconsistent, these equations are inconsistent and one cannot find a solution to this problem of Ax equal to b. So, that finishes the case where the number of equations and variables are the same. So, till now we saw the case where m equal to n. Now, let us take the second case where m is greater than n. Since m is greater than n, this basically means that I have more equations than variables. So, this is a case of not enough variables or attributes to solve all the equations. Since the number of equations is greater than the number of variables, in general we will not be able to satisfy all the equations. Hence, we term this as a no solution case. However, we still want to identify some solution which makes sense and which we can generalize for all the three cases. So, what we are going to do is we are going to identify an appropriate solution by viewing this case from an optimization perspective, and I will explain what that is presently. Let us look at a solution to Ax equal to b when the number of equations are more than the number of variables. As we mentioned before, we are going to take an optimization perspective here. When we try to solve Ax equal to b, we can write that equation as Ax minus b, and if there is a perfect solution to the set of equations, then Ax minus b will be equal to 0. However, since we know that the number of equations are a lot more than the number of variables, there might not be a perfect solution. So, what we want to do is we want to identify a solution in such a way that Ax minus b is minimized. Why do we want to do this? Notice that Ax minus b is a vector, and if you take each term in that vector, you can think of each of those terms as an error in an equation. So, to give you an example, if I have a11 x1 plus a12 x2 equals b1, a21 x1 plus a22 x2 equals b2, a31 x1 plus a32 x2 equals b3. Now, if I had a perfect solution x1 x2 which will satisfy all the three equations, then when I write this as a11 x1 plus a12 x2 minus b1, this will be equal to 0. However, when I cannot find a perfect solution, then let me call this as an error in this equation. Correspondingly, I will have an error in this equation, I have error in this equation. So, you notice that there are 3 errors, as many errors as there are equations. So, how do we collectively minimize all of these errors? One thing to immediately think about is to minimize E1 plus E2 plus E3, but that would not be a good idea, simply because I could have E1 as a very large error in the positive direction, E2 as a very large error in the negative direction, and E3 as 0. That will still give me an answer 0. So, that is not a good answer at all. One way to do this is to collectively minimize all of them by minimizing what we call as the sum of squared errors. So, you take this example, instead of minimizing E1 plus E2 plus E3, you are going to minimize E1 squared plus E2 squared plus E3 squared. In this case, notice irrespective of whether E1, E2, E3 are positive or negative, as long as they are away from 0, the contribution to the error term will be high. So, it will automatically ensure that you do not go very far away from 0. Now, this is the least squares solution. You could also minimize, instead of E I squared, you can minimize modulus E1 plus mod E2 plus mod E3, because mod is always positive. That is also possible, but in general we are going to talk about least square solution, where we minimize this sum of squares of errors. Now, this is the same as minimizing A x minus b transpose times A x minus b, simply because A x minus b is E. So, A x minus b transpose is E transpose E. So, if I have numbers E1, E2, E3 transpose and multiply by E1, E2, E3, this will lead to E1 squared plus E2 squared plus E3 squared, which is the same as this right here. So, minimizing this is the same as minimizing A x minus b transpose times A x minus b. So, the optimization problem is minimize A x minus b transpose times A x minus b. After some algebraic manipulation, we can write this objective as a function of the solution f of x. We observe that this optimization problem becomes a problem where the objective is a function of x. Solving this optimization problem will result in a solution for x, which is what we are going for. So, the way to get the solution to this optimization problem is to take f of x, differentiate it with respect to x and set it to 0. So, differentiating f of x and setting the differential to 0 results in the following equation, and this can be simplified to this equation, where A transpose A times x is A transpose b. Now, to solve this equation, we will assume that all the columns are linearly independent, which allows us to take the inverse of this matrix, and then we can come up with the solution x equal to A transpose A inverse A transpose b. While this solution x might not satisfy all the equations, this solution will ensure that the errors in the equations are collectively minimized. So, this is an optimization view for case 2, where the number of equations are more than the number of variables, or m is greater than n. We will conclude this lecture at this point. What I will do in the next lecture is take an example to illustrate what happens in case 2 in terms of how you get a solution and whether some of these equations are satisfied or not satisfied and so on. And after that, I will move on to case 3 and show an optimization perspective for solving those types of equations where the number of variables become greater than the number of equations. And then in the next lecture, I will also show how all of this can be combined into one elegant solution through the concept of pseudo inverse. Thank you.